I'd like to work a concrete example of this ceiling function radical expression. So let's start out with a nice number here. Let's say x is equal to 64 over 27. Okay. Now notice that 64 over 27 is a number between 2 and 3. 2 times 27 is 54. So 64 over 27 is a number between 2 and 3. Now let's apply that to this. Now, so the ceiling of a number between 2 and 3 is 3. So I'm going to put a 3 right here as the index of the radical. Okay? Makes sense, folks? Again, x is equal to 64 over 27. This is equal, of course, to something nice. 4 cubed. 4 over 3 quantity cubed, I guess we should write it that way. It's a little nicer. Okay. Now, so what we get is that this is equal to, again, designed to work out nicely just for illustrative purposes, so that we have 64 over 27 right here. And the cube root of that by this representation right up here is 4/3. So kind of neat, kind of a neat, I haven't seen this much. I thought of this the other day and just wanted to, I don't know how much this type of problem has been even worked. But anyway, this is a concrete example of the ceiling function functioning as the index of the radical. Now, our more general question right here is, how many real valued x satisfy this equation? Notice this is exactly in the same form as this, except we just have a constant out here, 7 over 5. And I have the definition of the ceiling function here, which I used actually right up here to establish that 64 over 27 had a ceiling of 3. Okay, now let's move along and see how this goes. We know that the answer has to be in this kind of form here, where n is a positive integer or a natural number. Okay, and I use n, capital N, to be the positive integers. Some people quarrel about that. Some people think 0 is included in that set. Others don't. I'm talking about the positive integers here. Now, so we know the answer has to be in that form. And I'm gonna omit the interval 0, 1 because if x is between 0 and 1, this just reduces to x, which is kind of trivial. And so 7/5 is not in the interval 0, 1. So I'm just going to skip straight to the interval 1 through 2. Okay, and I've written down the solutions here. Now, what's important here, I won't go through all the arithmetic with you. The thing that turned out to be important is that 7/5, and it came into play on these other ones, 7/5 squared is less than 2, right? Which turned out to be kind of useful. Okay. Of course, this is less than 2 because this is 49 over 25, right? 49 over 25 is less than 2. So that we see that the floor or the ceiling of this number is 2. That's why this would be a solution, right? It'd be the square root of 49 over 25 would be 7/5, right? Okay, in a similar fashion right here, it's easy to see that the ceiling of this number is 3. See, 3 ceiling. Okay, now here it's not quite as clear, but if you use the fact that this is just the same thing as 7/5 squared, squared again, right? I'm going to overkill right here. But you see, that means if 7/5 squared is less than 2, then 7/5 squared is also less than 4, right? And so that means this would be another solution, okay? So these are the 3 green solutions that I found. Okay, so the answer so far is 3. Now, I didn't work this out completely, but it's easy to note that 7/5 to the 5th power is greater than 5. Okay, and again, I won't go. It's slightly tedious, but we already know that 7/5 to the 7. We already know that 7/5 squared is a number very close to 4. Okay, and then if you multiply just you can go through it. 4 times 7/5 would be 28 over 5, which is bigger than 5. And that's an approximation, but it's hopefully convincing. So these are the only 3 solutions, okay? These are the only 3 solutions, and so the answer is 3. You know, to me, I think it's a super cool problem. Answer is 3. That's what I got at least. Now, I didn't prove it that it stops. Once I went to one that it didn't work on, I just stopped. But I believe the answer is 3. Pretty sure the answer is 3. But again, I don't make any claims. I've been wrong before, right here, I think this thing increases and starts to decrease over time because you see you're taking roots. And y'all, I think something that may be relevant here is the limb as n approaches infinity. This is a famous result from Rudin's textbook, I think. The nth root of n approaches 1. So you see, this thing is tapering off. There's no doubt it's tapering off because the function itself would approach 1. Okay, so hopefully this will convince you that once we get to a spot where this happens, that's going to happen the rest of the way. And there's probably a more formal way than even this, but this right here can be proved with the binomial theorem. So anyway, that does it, folks. I stand by my answer of 3. Let me know if you catch any errors in my thinking.